We'll switch gears now and start focusing on the Unix shell. We'll leave Python behind for just a little bit to get a better understanding of the programming language that we can utilize in the Unix shell and the existing tools and how we can leverage that for data analysis and automation of these processes. The question that motivates this is whether or not there is a computer environment that makes it easy to automate processes. One of the best ones to do that with is the Unix shell, or a terminal environment, that provides a slightly different user interface than what many of you are likely used to. It may seem at first very archaic, but it is incredibly flexible and allows you to kind of unleash the data analysis power of a lot of pre-existing tools. The shell has its roots in the Unix and Linux operating systems, and the philosophy is kind of built around the interface that you'll be dealing with, which is to keep things minimalist, modular, and very robust. And all of that comes with this funky user interface that we'll get to know today. Peter Salis, a computer scientist and linguist, suggests that we write programs that do one thing and only one thing, but they do it extremely well. We also write programs then that work together. So you do one thing extremely well, and you can work with another program that does its thing extremely well. And if you need both of these abilities executed in sequence, you write them in a way that they handle text streams because it's a universal interface, and you link them together through that text interface so that the product of one program is text, and the second program can take in text and work on that to create its output. How do we get this environment? Well, I mentioned that Unix and Linux operating systems come with this philosophy and shell environment. Mac OS is derived from Unix. It has a terminal application that emulates a terminal, so you can find all of the tools in there. Windows comes with various emulators. You can use something like VirtualBox, or in more recent Windows versions, you can activate the Windows subsystem for Linux. Jupyter Lab, which we use in this course, comes with a terminal interface that we'll be leveraging heavily for labs, exercises, and homework. In most instances, it comes in the box in Windows. You have to jump through a few hoops, but for the purposes of this class, we have everything that we need. So what does this look like? I include a bunch of screenshots here from the Linux environment that I'm working on. So you can see here, this is a terminal window. We'll describe what all of this text means in a little bit, but here I typed in a command, ls. When I hit enter, it lists the files in the directory, and they're all differently colored. It all means something. Blue is that we have directories. There are some files that have certain characteristics, and that coloring is kind of optional depending on what your shell environment is capable of. I can move around in the directory tree, which we'll talk about. Here, I use a command that is called cd, change directory, and I want to enter the directory lectures, which I see here, and then I want to list all the files that end in tex, which was the previous format that I made my presentations in, LaTeX. You can see that there's hopefully a familiar naming scheme here that you have been exposed to in this class. And by the way, all of this is available in the GitHub for this course, which is GeosF636_pag. So you have these files and the directory structure in your Jupyter Lab environment. Now we can do something else. We can use a command that we've seen in some of the slides, which is echo. dereference a variable that's called shell here. The login shell is the program bin bash. So the shell itself is a executable that lives in a directory of executables in the Linux environment. You see that the interface is text-based. It interprets your commands. Coming from Python here now, you can think that this is a continuously running interpreter that is just waiting for you to issue the commands or the functions and programs that you write yourself. There are various different flavors. Some of the more popular shells are Bash, the born-again shell, or the T, C shell, or just the C shell. They distinguish themselves from each other through a different syntax of how we can deal with if statements and for loops that we'll look into a little bit. The shell defines your working environment. So within each shell, you have a set of global variables like this shell variable, for instance, and a few others defined. We'll look into that at some point too. Now, first, we want to understand this command line a little bit better. Let me jump back here. You can see that there's some perhaps cryptic looking text before $sign where I issued my command. And all of this we kind of call the prompt. So everything that is before a $sign or some other, I often use greater than sign to indicate the prompt in my examples. But all of this is the prompt. If I go back once more, there's a username at a machine name. This is my laptop. This is my username, colon. And then there's the current working directory, which is in the home directory, tilde, and then work teaching 2020 GEOS F636_pag, and then $sign. All of this is my prompt, and the prompt can change from setup to setup, and you can configure your prompt if you so desire. Ask Google how to do that. Okay, after the prompt then, there can be a command. Here it is rm, remove. In my examples here, I had ls or cd. And then there may be options. Options are optional. Here we say -f. They generally start with a single dash or a double dash. Single dash is usually one letter. Double dash is a longer text that you can use. And these options obviously depend on the command that you're using. The command defines the options that it allows for. We'll look into that a little bit later too. And then there's foo.text, which is the argument that is given to the command. So what this line here means is that remove foo.text forcefully. So even if there are file parameters that would prevent you from deleting it, you absolutely want to get rid of it. At the end here, there's the cursor that indicates where you might be entering additional text. So going back here, right, ls doesn't have any options given, and the argument is asterisk tech, and we'll look into the wildcard a little bit later in this lecture. Basically, it captures everything that ends with tex, right? As you can see here, all of these files that are listed end in tex. So diving in a little bit deeper into the shell command anatomy, here again, we have ls as a command name. There's a flag or an option given with a single dash, meaning -l. Commands aren't necessarily limited to take only one flag or argument. Here is another one given. Here, this is indicated by a double dash and the long name of the argument with some value. So these might occasionally take values. And then there's a positional argument, or the argument that you give. So what this says is list the long format of the contents in the home directory documents folder with indicating the block size as kilobytes. If you don't know, which is natural, what the arguments are or what programs do, you can use the man pages, the manual pages. You can issue the command man space, and then the command name that you're interested in, here mkdir. A help page like this is showing up with initially the name, mkdir. It explains what it does. It makes directories, gives a synopsis. So there's mkdir, there's some options, and then the directory name that you want to make. It creates directories if they don't already exist, and you have some options. -p is quite useful if you want to create a directory hierarchies and create the parent directories as needed if they do not exist. Many, if not all, commands come with a help flag. That could be -- help or just -h. This is built-in help that is often designed as a quick reminder of what a program can do. So if we use mkdir -- help, we see what the usage is, what it does, or what the flags are that can be used, and what their description is. This is incredibly useful if you just need a quick reminder. And then obviously there is the internet. If you have something specific in mind or the program that you want to use has a fairly complex syntax or list of options to achieve what it is that you want to do. The environment is something that I mentioned before. We already use the path variable that I label here in red. This is the result of issuing the env command. So on the command line, we can say env, and that gives us our entire environment. So these are all global variables. You can see here, username is given here. Many other things in addition to the path, which is a list of directories. The path is incredibly important because that is the list of directories where the shell tries to find programs. So when you write your own program, you should save those in a directory that is in the path. And then instead of giving the shell the entire absolute location of where your program is to execute it, you can just use the short program name. The shell is going to find it for you by looking in the path. To set the path variable, you can say set env path, and then path to some directory, and then you separate the various directories with a colon, and you always put your directory in front, hoping that you're not creating any issues. And then you append at the end the existing path variable. And here are the two different syntaxes for bash and tcsh. So you can see that in bash, we say export path equals all of this, whereas in tcsh, we use the set env command, space path, space, some directory, and then the existing path variable. In summary, the shell tries to execute what you type as a command. Here, the rm command is given. This is a built-in command for the shell, so that is going to be executed or found first. The shell maintains a list of all locations of executable commands, including what is in the path, which specifies location of where to find commands or programs. The shell traverses this list in order. If you've got two programs with the same name in different directories, only the one in the first directory will be called. This is a common problem that you might write a program that is called test, and there's a built-in shell command that is also test, and you cannot override those. So if the program doesn't do what you think it does, you can always test it by including an extra echo something and see whether you can find it in the output. If that's not the case, it's likely that you execute a different command. Path variable can be permanently set in a config file for the shell, which is .bashrc or .tcshrc that live in the home directory. It's usually /home/username. And when you first start a terminal, that's where you end up in. And these configuration files live in there. They start with a dot because that hides them from the default listing of the ls command. Let's look a little bit at file and directory organization. I mentioned that files and directories are organized in a tree or hierarchical structure. You need to specify names by typing them. There's no clicking. The shell or the terminal environment is not sensitive to any clicking other than highlighting and right-click, copy and paste the name, but you cannot double-click on this PDF here, for instance, and hope that it opens up the PDF viewer. You will have to say on the command line, acro read, or whatever your PDF reader is, and then give it the file name as an argument, and that will open the window of your PDF reader. Something like tab completion is useful. Often you can start typing the file name here, 2018 _, and then use the tab key on your keyboard. If the beginning of the file name is unique, the shell will complete the entire file name and you just hit enter and you're done. If it is not quite unique yet, you will get a listing of things that are possible options, and you can just complete and hit tab. Important is that everything in the shell is case sensitive, meaning that here the word case in lower case letters is not the same as capital C, lowercase a, capital S, lowercase e, or everything in all caps. So this makes a huge difference here, right? I could not find this file if I started it with a lowercase v. Case sensitivity is very important. There are some special directory symbols. Dot is the current directory, dot is the parent directory. So that's, you go into a directory, say cd maps, and then ls, and you look what's in there, and you don't find what you want, and then you say cd ... and you go back out to the top hierarchy directory. And tilde is the home directory, which is where most of your stuff should live. So you can always say cd space tilde and make it back to the home directory. In this graphic over here, you can see there's a command that's called tree that may or may not be installed. If it is in a directory, so here I'm in work, research, projects, bias, and I say tree. In that directory, there are 1, 2, 3 subdirectories, literature, maps, and permits. And in these subdirectories, here there's one file that's a PDF. There are 4 files in here and no additional subdirectories. And here there are 3 files. So it tells you there are 3 directories, 9 files that are found in total. But that should hopefully drive home the idea of the hierarchical tree structure in which directories and files are organized in this environment. One thing that is a little tricky is finding the actual commands that exist. You can always ask Google. Here's a starter list. I'm not going to go over all of these. You have them in the slides, but I showed already ls list directory contents, pwd print the working directory if you got lost and you want to know where you are, cd change directory, cd ... change one level up, make directories. You can move files. This is renaming. So here we're moving test to dummy, rename test into dummy. So after that, there's no more test file in this directory, only a dummy file. You can create empty files with touch. You can move files into a directory. So if dummy were a directory, then things end up in here. You can also copy with the copy command. and copy recursively, remove recursively. You've got to be very careful with the remove command. If you work in the shell environment, there's no trash bin. So once you say remove here recursively, which is a flag that is necessary if the argument is a directory, if you say remove -r this directory or that file, this will be gone. You will not be able to recover it unless you do have a backup copy somewhere. So be careful with the remove command. This is very terminal. Some other useful commands are, the man page command, less, to look at the contents of a text file. If you use this and open a text file or just look at a text file, you can exit it by typing Q to quit. I can look at the beginning or the end of text files without really opening them. You can count words, lines, and characters in a file. You can concatenate files and sort them. This is all quite useful in various scripting settings. Let's get to the wildcards that I mentioned before, because very often you do want to match multiple files at once. For instance, here, all the files that end in .py. I would say move mv *.py to listings. And listings is an existing directory. So what's happening is that all the files that end in .py are going to be moved into a subdirectory listings, and then they live in there. So here in the subdirectory listings, I can issue the command ls *.py to see all of the examples that are Python scripts that live in there. You have access to these. You can look at them. Now, note that this example MV here will not match NumPy, for instance, because we do require this dot. So we want everything that has the extension .py to be in listings. As useful background, wildcard recognition expansion is called globbing, stems from the glob or global program, which initially did this. This is now built in to the shell. I bring this up because if you want to do something similar in Python, that's the search term that you would be looking for, globbing. And there's a library glob that you can import that helps you realize this kind of functionality. There are two types of general wildcards. One is the asterisk, which matches 0 or more characters, and the question mark, which matches exactly 1 character. So here's an example. We can say ls question mark dot asterisk, which lists everything in the current directory that starts with 3 characters, has a dot, and then has 0 or many characters afterwards. So we see here we get bnf.text, gmt.conf, gmt.history. Everything before the dot has 3 characters. Afterwards, there are some, but it doesn't matter which ones. Another example is ls question mark dot log. And in this case, we look for files that end in .log and have only 1 character, and we get x.log. You can use other pattern matching expressions here. In the square brackets, A to Z in lowercase matches all lowercase letters, and uppercase matches uppercase letters. This matches both lowercase and uppercase letters, and here we're going to match numbers. So as an example, we can say ls, everything that starts with letters that are lowercase a through g, and then whatever other letters there may be, and ends in .py. So we get dict underscore example, which starts with a D, which is between A and G. F is between A and G. So for break example.py, for example.py, get grades, grades 2, and grades.py, right? They all start with some letter between A and G inclusively, and then have however many letters afterwards, and then in .py. We can also say ls, everything that has at least 1 number in it. So here we can find grades 2, output 2, grades 2, output, grades 2. So all of these files have at least 1 number somewhere in their file name.